order of today's presentation. We have 4 teams for live presentation today, and 2 of them said they are not available this time, so they will post the recorded version of the presentation today. So the number 1 team is the SQulRL, I should say. The presentation will be Sang-Han Song, and he will talk about the quantum algorithm for tight binding model and its implementation. Sang-Han, could you share your screen if you have one?
Sure.
Okay, I can see your screen.
Sounds good.
Seems like you should swap the display. It's the presenter's view. We're seeing. So you can click the display setting here to swap the presentation.
It sounds okay.
Still, we are seeing the presentation view.
Yeah, we can see your notes. That's the problem, I think.
Yeah, the upper one. Yeah, click the upper one.
Right.
Yes, great.
Okay.
So Mike, it's yours.
Okay, so let me start. Good morning and good evening, everyone. This is Team Squirrel from SKQU, and I'm the team leader, Sang-Han Song. We have prepared the presentation about what we did during this mentoring program with the thesis quantum algorithm for tight binding model and its implementation. We chose this thesis since we expect quantum computer to contribute a semiconductor industry successfully by simulating electronic band structures in the quantum manner. We will first talk about what tight binding model is and discuss our algorithm and code implementation to get the result. Then we will wrap up with showing how well did we get the dispersion relation in each ideal and noisy environment using IonQ backend simulator. Our work is based on the paper on the right side. So what is tight binding model? Tight binding model is a well-established quantum approximation model which explains the electronic band structure in a certain crystal lattice. For example, if we consider 1D diatomic chain structure and assume there is only 1 electron per 1 atom, we can think the entire energy scheme on our system with the on-site energy as well as electronic Hoping energy. Here, our Hoping dynamics only deals with Hoping between nearest neighboring atoms, and therefore, we can set Hoping term matrix data T0 and T1 properly. The exponents of Hoping term 0 and 1 each means internal Hoping inside the unit cell and external Hoping to the neighboring unit cell, and the same logic is adjusted to the Hamiltonian representation. Each Hamiltonian term for tight binding model can be represented with the tensors of terms representing electronic orbital Hoping of state beta to state alpha, and site Hoping of site V prime to site V multiplied by the Hoping component. Then, how can we implement this model to quantum algorithm? This slide shows the entire scheme of our algorithm. It is basically based on VQE, which has the objective tight binding Hamiltonian we said before, and registers encoding orbitals and site. We sweep the eigenenergy value with respect to momentum quantum number p, of which the magnitude of k vector will be 0 to 2 pi over lattice constant, and we update parameters at each step for the energy level I. And then the same iteration process is proceeded for the upper energy levels in our interest. For orbital register, we represented each atomic orbitals with 1 hot encoding. In order to get the quantum state of linear combinations between one-hot bases, we use number-preserving ansatz for nearest neighboring registers, as you can see below. This number-preserving ansatz only deals with the probability amplitude for one-hot bases and set other bases to be zero. First, we optimize the parameters of the ansatz of a lowest energy eigenstate. And then we optimize the ansatz for the first excited state with already optimized ansatz for zeroth eigenstate with fixed parameters. This sequence ensures the orthogonality of each level's eigenstate and therefore gives the independency for optimization at each energy level. Then how about site register? Due to the Bloch's theorem, single electron eigenstate can be represented as a quantum Fourier transform formalism. So if we consider the specific momentum quantum number P for the periodic lattice system, binary represented P number is an input for the QFT circuit, which ensures the Bloch state of an electron. Hamiltonian for our algorithm is a set of Pauli string decomposed elements similar to the Jordan-Wigner transform. Since we have the hermeticity and symmetry in our Hamiltonian, we could simplify the entire Hamiltonian into the sum of real part tensors and imaginary part tensors. Now, we have Pauli string decomposed Hamiltonian and the parameterized orbital and site ansatz, so we can run VQE. We used Cobile optimizer and constructed data structure which stores the optimized parameters and eigenenergy for each iteration steps so that we can reuse the parameters for the orbital register update and draw the energy momentum relation diagram. Let me explain our code architecture for the model simulation. We made the tight binding model implementation Python module called tbm.py. Input data are number of qubits for orbital and site register, Hoping term matrix, crystal lattice dimension, and the simulation mode ideal or noisy. Ideal mode gives the ideal calculation result based on Qiskit simulator, and noisy mode gives the IonQ ARIA 1 backend noisy simulator result. Through tight binding model dash Hamiltonian class, we get the dictionary data structure of real and imaginary part of Hamiltonian in the sparse Pauli OP form. These data are used in running VQE at tight binding model dash VQE class and update parameters and ansatz with respect to momentum quantum number P and energy level I. All the parameters and eigenenergy values are stored, and finally we can get the energy momentum dispersion relation. From now on, I'll show you the final result. These are our EK relation for 1D monatomic and diatomic lattice structures with the magnitude of K vector to be 0 to 2 pi over lattice constant. All the simulation results on the left side perfectly fits with the desired result. For the 1D monatomic lattice case, since we are dealing with the situation that one electron per one atom hopes, lowest energy level occupies the negative side of sinusoidal function, and the first excited level occupies right above side of the sinusoidal function. For the 1D diatomic lattice case, left half side of our result and the right half side of desired results have same form, so both diagrams are physically identical. This is our result for 2D hexagonal monatomic lattice. Tracing the x-axis, the momentum vector aligned the x-axis of desired EK relation and its vector magnitude, we can identify that we obtain physically identical EK diagram with the desired one. Moreover, we obtain 3D EK relation for 2D hexagonal lattice. Projecting the 3D diagram onto YZ plane, we can notice that the graphic we've seen before is moving in parallel through the X plus Y axis. So we could identify the 3D dynamics of hexagonal lattice energy momentum relation. We also tried to run the algorithm on IonQ IRL1 backend noisy simulator. First column shows ideal simulation results. Second column shows noisy backend simulator on only orbital register. And the third column shows noisy simulator on both orbital and site register. As you can see, noisy simulations for all registers have much more fluctuations in the diagram, and we think that it is due to a lot of controlled rotation gates at QFT part on site register. To conclude, we could completely simulate tight binding model for various types of crystal lattice structures. And since there are significantly large error as number of controlled rotation gate increases, in order to successfully simulate the tight binding model on quantum computing hardware, we expect to reach higher gate fidelity accomplished in the near future. This is all of our presentation. It was Team SQulRL, and thank you for listening. And we especially thank our mentor, Miguel and David, for managing and giving us advice during the mentoring period. It was a great honor. Thank you.
Thank you for a nice talk. Any question from the audience or mentors? I have a quick question about the backend simulation. So how many qubits have you used, and the how many C rotation gates you had in your circuit? Someone, you are muted, or you're checking some numbers there.
Sorry. Yeah. We used entirely 7 qubits for this algorithm, 2 for orbital and 5 for site register. The quantum Fourier transform for 5 qubits, there may be, wait a minute. There may be 10 controlled RZ gates. Yeah, we use 10 controlled RZ gate for QFT for 5 qubits.
And that means the 20 C0 gates for the Fourier transform, and you use the C0 or XX gate for that, XX pi over.
No, we haven't used C0. We use just Hadamard gate and controlled Z gate with the parameters for 2 to the n, and the swap gate for the construction.
I see. Any other questions from audience? Yes, David.
Hey, Team SQulRL. Well done. I had a question for you if you stay on this slide. So I guess my question for you is on the 2D hexagonal monoatomic lattice. But what do you think this would be a good model for? And could you compare it to something that's, like a real system?
In the real world, 2D hexagonal monatomic lattice is a crystal structure for graphene film. So since we simulate this structure, we can get the energy momentum dispersion relation for the graphene structure for thin one layer film. Yeah.
Awesome. Yeah, I think so too. I think it'd be interesting maybe to plot, to look at maybe the band diagram that you have here, both in maybe in the ideal case and the noisy case, and see if the splittings that you have, the band gaps that you see, match
Yeah.
what you might see in real graphene, or if you can get the band diagrams in general, it might be interesting to plot that against either experimental data or other kind of classical models, in addition to your like the ideal model, but some other band structure calculations.
Our model is based on the graph in the paper we used, and actually we haven't compared the real complex energy dispersion relation in the like a Google, but yeah, we just compared our result with the result in the paper.
No, I think that's great. I think you guys did a great job. I was just saying in that one, you could compare to a real system to kind of check it out. Albeit the graphene system is complicated and I don't think it behaves like a tight binder very well. It has like
Mm,
I mean, you can kind of see it. You have very straight lines in your dispersion curve where normally they're parabolic.
yeah,
Um,
right.
so those are some things that you could compare and see how the model does.
Okay.
Thank you guys. Well done.
Let's thanks to the speaker again for the nice talk. Let's move on to the next presentation. So the next presenter will be team OptTrot, and the presenter will be Hyun-Sung Kim. So I see him here. So hi,
Yes, I'm here.
could you share your screen?
Yeah. Yes. Um,
Okay, it looks great.
okay, it's okay for everyone. Wait a second. Okay, nice to meet you, everyone. I'm Hyun-Sung Kim, participate with the OptTrot team in the IonQ mentoring with the Dr. Ray mentor. And today I will introduce the trotter circuit optimization library, the OptTrot, the design philosophy and usage during the we did in the mentoring season. So OptTrot is basically optimizing the trotter circuit kit library for the gate model quantum computer. So it provides a various routine like the decomposing the Hamiltonian into several Pauli elements and graph optimization tool and the circuit synthesis routine. So when you want to optimize the trotter circuit for time evolution on the gate model computer, well, there are various methods to optimizing the circuit, but about the time evolution circuit, we need the require the decomposition routine, and from the decomposition, we have to clustering each Pauli element to the commuting partition, and based on the commuting partition, we have to generate the optimized quantum circuit. So these all processes are the composition of various routine, and in practically we have to combine the various library. So in OptTrot library, we want to so there's some unified version of the DSOL process, and we developed this unified version and circuit synthesis library development during the mentoring. So I will explain the what process we are aiming to in the OptTrot and the basic theory of the design. So when you want to generate the time evolution process in the gate model computation, we have to mimicking the time propagator operator with the discrete the quantum gates, right? So about the trotterization, it is so in the standard the process to make a trotterized circuit for time evolution is first to construct a single Pauli element evolution gate. For example, in here, these two quantum circuits are corresponding to the Pauli Z1, Z2, and Pauli X1, X2 Hamiltonian for each. So usually we combine these two circuits, the sequentially, we generate the more complex Hamiltonian on the gate model. But the problem is that just concatenating these circuits generate the two deep circuit for the gate model computer. So usually it is not practical for very complex Hamiltonian. So our question is that what if we modifying the quantum circuit in the below one, then what Pauli element would be corresponding to the Hamiltonian? The answer is the same. The design process is generating these kinds of the circuit from the given Hamiltonian. We can reducing the left circuit to the right circuit. So the reason why we can using this optimization direction is that these two Pauli elements are connecting to each other, so we can parallelly applying on the quantum circuit the rotation. So the problem is using this method. To use this method, we have to know all the Pauli term after the circuit applying the controlled or the transformation gates each. So we have to chasing every Pauli term in every single step of the circuit. Now, this process was about the solution was suggested by in 23 the Smith et al. Paper. So they using a Pauli prime method to accomplish this action. So this is one example of a circuit optimization. I will explain the Pauli prime. So Pauli prime is a collection of the two n number of Pauli element of the n number qubit system. So this is just the arrange of the Pauli element. So the left column is indicating the Pauli element when we applying the rotation jet gate on the circuit, then what element would be rotated on the circuit, and the right side is Pauli element when you applying the Hadamard gate on the circuit, the wire, then what Pauli element would be came out on the circuit. So when you applying the Hadamard phase and CX gate to the Pauli prime, we can make the corresponding action on the Pauli prime. So these are example of chasing the Pauli term using the Pauli frame. First of all, the or quantum circuit start with each corresponding Pauli Z and X elements at the beginning. When we applying the CNAC gate or Hadamard or phase gate, then these Pauli terms are mixed and appeared on the Pauli frame with different shape. So using these terms, we can chasing every Pauli element on each rotation step. So for example, if we analyzing the previous quantum circuit with Pauli prime method, we can see how we accomplish the Hamiltonian time evolution with the trotterization circuit. So the controlled NOT and Hadamard and S gate is preserve the Pauli prime, so we can using these gates without any consideration the distortion of the quantum circuit. So, but in this perspective, we can see the direction of the optimization. So these two circuits are identical for time evolution, but the frame path, the frame step, it means the frame, from one frame to the another frame step these are different. So in this quantum circuit, we step the two different Pauli frame in the intermediate step, but in this quantum circuit, we only require the one Pauli frame. So it means we choosing the proper Pauli frame path, we could optimizing the time evolution of quantum circuit. but there is some problem. Actually, for the given Hamiltonian, the clustering the Pauli element into the commuting partition is itself an NP-hard problem. So before we using this Pauli pathfinding in optimization method, the construction, the environment optimization requirement is already a hard problem. So in the library, we choose then using the quantum optimizer to handle the job. So we implemented a very popular the annealing system interface to the library. When the Hamiltonian was given, if you have the D-Wave, the API key, then you can just simply type the one line. You can clustering the Hamiltonian terms into the commuting partition. So actually, the QSkit already providing the classical algorithm to accomplish this clustering. So we comparing to the classical problem and DA server, but for the case, the quantum annealing system is show the more accurate result and more proper the direction of the Pauli frame optimization. So we made a commuting partition from the given Hamiltonian, and we have to find the optimal path between the Pauli frames. But the problem is there are tons of the many Pauli frame for the qubit system, and the figure in here is an example of the Pauli frame map, and it is just a 3-qubit system. And so our job is finding the correct frame path for the corresponding Hamiltonian. But this problem is even harder than just clustering the Pauli frames. It is called the traveling purchase problem. And the original author in 2023, they did not solve the exactly what is it NP-hard problem. So they used the dynamic programming method to find the optimal path. So there are nine types of clipboard transformation between one frame to the another frame. And they search the all possible routine of the Pauli frame and find the optimal path. But in the library, we found some better solution to find the path between one frame to another frame. So in the original paper, they can only search the nested Pauli frame path, but we found that if the Pauli between two Pauli frame satisfied some specific condition, then we can find the direct path with only the two frames. So these are example of this process. So for example, when the Pauli elements only consist of identity and Pauli jet element, we call them to the IZ family Pauli element. So this is an example. When the Hamiltonian only consists of the IZ family, for example, the QAOA and such system, then we can only using the C control the NOT gate to one prime to the another prime. So if we using the symplectic representation of the Pauli element, we can represent every Pauli term into the two integral tuple. And then using the representation, then we can make some the corresponding algebra on only the binary representation. Then so when we want to achieve the IZZ gate Pauli element from the one plane to another plane, so the left side is the current Pauli plane, and we want to make the B theta, the plane. So we have to make this be the new frame is based on the current frame method. So intuitively, it's just a simple. We only make the applying the control the NOT gate from between the first and second line. We can achieve this powered frame. So using the symplectic representation, we can change the power plane representation into the binary vector representation. So then, when we have the new power element, we can represent this element as a combination of the current frame element. It's like representing with the linear combination. Then just to simply solve the linear equation, we can find this representation. And then this representation, we can find the what transformation needs to achieve the new frame from the current frame environment. So summarizing, using the binary representation, we can find the clipboard, the CNAT gate composition. We only solve the simple linear equation solve. So these are about the one Pauli element. If we require the new Pauli frame, which is all the Pauli elements are new from the current frame, then just simply find the representation of the new frame and find the transformation into and just decomposing the transformation matrix into the LU decomposition, then we can find the corresponding CX map to accomplish the new Pauli frame. So these are example of the previous these are example of the CNAT gate transformation so we found. So the problem is this process only used for the IDET family, but if between the two Pauli frames satisfying the prompt Pauli elements are all mutually commuting, then we can use the same algorithm to the general Hamiltonian. So these are algorithms we implemented in the our OptTrot library, and this algorithm only the applicable for the commuting Hamiltonian, but show the better result than the standard version. So for example, we testing the 4-qubit system with the diagonal Hamiltonian. The standard trotration requires the 29 number of CX gate and 32 circuit disks, but using the OptTrot library, we can find the reduced CX gate and reduced CX gate and more shorter disk circuit. So verify that this evolution the CX map, we tested the circuit system using this circuit as an ansatz and conducted the QAOA algorithm. And we tested for the 400 number of random Hamiltonian with next ansatz. And for all Hamiltonian, we reached the ground state with smaller than the 0.9 decimal evolution error. So these are example of the result. So the further plan of the OptTrot team is that the current library only support for the commuting Hamiltonian. So we have to find for general Hamiltonian consists of the non-commuting Pauli element. So we have to develop more the non-commuting frame routines, and in optimization viewpoint, we suggest a solution for finding a path between two Pauli frames. But what was exactly the optimized path was still unsolved. So we have to have the more the research and the development would be required for the better library development. So this is the end of the OptTrot team, and thank you for the Dr. Ray during the mentoring, for the 2 months mentoring, and thanks.
Thank you for a nice talk. Any questions from the mentors or attendees from here? For me, it was a little bit difficult to understand.
I'm sorry.
Yeah, couldn't make it questions. Any questions? But yeah, I can see you. Yeah, the team worked really hard. So yeah, thank you for like the nice presentation. If there's no questions about the presentation, let's move on to the next speaker. Thank you again. And next speaker will be Team World Cup, and the presenter will be Min-jae Ju. And is he here? Oh, I can see him.
예.
네.
제가 좀 미리 녹화해 둔 걸로 혹시 대체해도 될까요? 지금.
그렇게 하시죠. 예.
네.
그거 틀으셔도 됩니다. 예.
어.
Hello everyone, my name is Jeju from
소리를 조금 더 키워주시겠어요? 잘 안 들리네요.
네.
소리가 좀 작아서요. 아니면
네.
화면에서 소리를 공유하도록 해주셔야 될 것 같은데요. 공유를 하실 때. 지금 거의 들리지가 않아요. 그쪽에서 아마 그쪽 마이크를 타고 가거나 하는 것 같아요. 이제 화면 공유를 하실 때 소리를 같이 공유하는 방법이 있거든요. 그렇게 하셔야지 소리가 제대로 들릴 거고요.
네.
그렇게 설정이 되어 있나요?
잠시만요. 죄송합니다.
제가 채팅창에 그 소리 공유하는 방법을 올려드릴 테니까 한번 확인을 해 보시겠어요?
네, 알겠습니다.
예, 우선은 저희 이제 다음 팀 먼저 진행을 하고 다시 돌아오도록 하겠습니다. So we had a little bit of problem with the sharing the video. So I will go. We will go first with the next speaker, which is the Q-PDE innovator, Dong-Yun Chung. Are you here? Okay. Let's see him. But yes. So yeah, could you start?
Okay, so first of all, apologies for the slides. It's kind of modified after we have submitted it on Sunday. So we added some visualization and just get rid of some of the mathematical details in our site. So if you guys have our previous ones, then there will be no problem like understanding the overall process. So hi guys, we are Q-PDE team and I'm Min Chung. And our presentation is about developing an efficient quantum algorithm to solve the Poisson equation. And this is the content. And so first of all, the Poisson equation is the well-known partial differential equation widely used in physics and engineering. And the reason why we are trying to tackle this in quantum manners is because ever since quantum mechanics was developed in the early 1900s, it was verified several times that classical mechanics is not able to simulate our universe within our tolerance. And several variational algorithms were developed to solve the Poisson equation relying on creative methods. But in this research, we propose using the quantum Fourier transformation inspired by the method of converting the Poisson equation through Fourier transforms to transform the overall process in a non-iterative manner. So the objective of this research is to introduce a hybrid and non-iterative algorithm using the QFT and classical matrix algorithms to reduce the overall computational cost.
Excuse me, sorry to interrupt. Can you move a little closer to your microphone? When you started, you were very clear, and now it's hard to hear.
Oh, sorry.
Or speak a little bit louder. Yes.
It's clear right now.
Much better.
Oh, okay. Okay. So yeah, so our research objective is to introduce a hybrid and non-iterative algorithm using QFT and the classical matrix algorithms to reduce the overall computational cost when solving a two-dimensional Poisson equation. And next, we compared the quantum operations included in the QFT-based method and one cutoff edge variational method introduced by Sato Yuki, published in 2021 in the PhysRev journal, to finally conclude that the QFT-based algorithm requires less quantum operations than the variational algorithm. So the mathematical backgrounds of the variational algorithm is directly adopted from Sato Yuki in 2021. And it uses the potential energy function of the Poisson equation. And using the central differentiation scheme shown in the figure here, the energy functional can be discretized using the discrete Laplacian operator A. And without loss of generality, we can assume that the magnitude of the source vector f is 1 due to the linearity of the Laplacian operator. However, we cannot do the same thing to the solution vector v, so we parameterize the v with r and theta, where psi theta is the quantum ansatz of magnitude 1. So substituting this representation, we get the E discrete with r and theta. And this differentiating with respect to theta, we obtain the optimal r that minimizes E. And substituting this optimal r again to E, we can fully parameterize E with only thetas that we can control throughout the quantum circuit. And we don't have to worry about any singularity of this cost function in the red box here, since the A matrix on the denominator is positive definite. It has 2 on the diagonals and -1 on the subdiagonals, a three-diagonal matrix. And moreover, in our case, we're dealing with 2 dimensions, so we have to replace A to A times I plus I times A, where A times I is the Laplacian operator along the y direction, and I times A is the one on the x direction. And for the variational algorithm, we prepare psi theta with the hardware compliant ansatz only constructed with layers of Ry and Rz and CNOT gates. And the expectation values are processed through classical computation to calculate the cost function. And with the classical optimizer, we use the Powell optimizer, gradient-free one. We generate another set of parameters to plug in the quantum answers and proceed iteratively. And the mass of the QFT-based one is not different from the classical analog that is adopted from Pan et al. In 2021. We apply Fourier transform row-wise along the x direction in the two-dimensional domain. Then substituting the Fourier transformed expression to the Poisson equation, we obtain a simplified matrix equation for each wave number. And in this case, only the Fourier transformation is conducted through quantum manners, and the matrix equation is conducted through classical matrix algorithms. In this section, we present the quantum circuits constructed for each algorithm, and for simplicity, we display circuits for 1D. For 2D, we have to double the number of qubits that are included in the quantum ansatz or the state preparation. So the circuit shown in this slide computes the denominator of the cost function, the psi, a psi, and the quantum operations included is shown in the table on the right for each n. And the circuit here computes the numerator of the cost function. And the source function f is prepared through the built-in function in Qiskit, the state preparation method. And for each iteration, we need to execute the circuit for the denominator twice because we're dealing in a two-dimensional space, and the numerator once. So the A operator is separated into two terms, A times I and I times A, as I explained previously. Therefore, the total number of operations included is shown in the table on the left bottom and plotted on the bottom right graph. And the circuits for the QFT-based algorithm, also the main issue in this algorithm is that we cannot directly measure the complex phase values of the Fourier coefficients. So we can only measure the probability amplitudes of the Fourier coefficients, not the exact phase values, but the phase values is important to proceed into the classical matrix algorithm. So instead, we measure the real and imaginary component values separately using the x and y variables. So if we want to measure the real component of some Fourier coefficient, then we just use the x observable on the first qubit. And if you want the imaginary one, then we use the y observable on the first qubit. And moreover, since the QFT block reverses the order of qubits, so for example, if you want the 6 Fourier coefficient in the 3 qubit state, then we want to project the QFT transformed state vector to the 110 state computational basis state. But since the bit is reversed, then in this case, we have to see not the second and third qubit here. And for any Fourier transformation, the zeros and n over 2's coefficient are always real. Therefore, we need to execute the QFT block n times 2n minus 2 times. So n is for each row, and 2n is for n for the real components and n for the imaginary components. And the reason why we subtracted 2 is because the zeros and n over 2's component does not need the imaginary component measurements. And since the solution vector is also assumed to be real, for the last inverse Fourier transformation, we only need to measure the real components. Therefore, this process additionally requires n squared times of executions. And additionally, the classical matrix algorithm is typically called the Thomas algorithm, which efficiently solves a tree-diagonal matrix. And it is an n-dimensional tree-diagonal system which requires n times 10n minus 11 classical operations. So the number of quantum operations included in the whole QFT algorithm is as in this table and displayed on the right graph logarithmically. And the slope is kind of high because the number of QFT blocks increases more faster than n squared as n increases. And in this section, we display the quantum simulator results with the ideal simulator of IonQ, setting the source function to the two-dimensional sine function, and the gradient-free Powell optimizer was used with the function tolerance and parameter tolerance set to 10 to the minus 4. And the initial parameters were initialized with the random number generator in NumPy. So the two-dimensional results here in the variation algorithm is our results for n equals 8 and 16. And the figure on the right is adopted from Sato 2016, the one-dimensional result was from the original paper. And the error of the 2D case seems to be smaller than the 1D case, but we have to consider that the range of the 1D case seems to be more larger than our case. So the 1D seems to deal with the 2 sign because the range is from -6 to +6, but ours is the solution of the two-dimensional sign, which the solution is 1/8 pi square sign. So you have to consider that when comparing the L to norm error. And the QFT-based algorithm was simulated for n equals 8 and 16 and 32. And additionally, we plotted the error convergence rate. But as you can see, the convergence rate does not follow exactly the power law because when plotted logarithmically, if it follows directly the power law, then it should display as a linear manner, but it's not typically linear. And this is because the number of measurements increases more faster than quadratic, with increasing n, which increases the randomness of the measurement for a larger n. And we have calculated the whole cost involved in the QFT-based algorithm previously, but for comparison, we need to additionally calculate similarly the whole cost in the variational method. So for this process, we need to know the average number of iterations required until convergence for the variational algorithm. To estimate the average number of iterations until convergence, we made a non-quantum analog of the quantum circuit only using linear algebra. And in this way, assuming that the quantum hardware we're going to use exactly aligns with our model, we conducted the same optimization using the Powell optimizer. And the average number of iterations for each n is shown in the table below. And we'll use this result to finally compare the quantum operations included in both algorithms. And additionally, since the QFT-based algorithm includes classical operations, we implemented a effective parameter that includes the number of basis quantum gates, the U1, U2, U3, and C0 gates, and the classical operations for the QFT. And the corresponding parameter for the variational algorithm simply asks the number of basis quantum gates per iteration. But you guys should note that CQFT is the cost included in the whole algorithm, while C variational is the cost included per iteration. So dividing CQFT by C variational, we can verify the upper limit of the number of iterations included in the variational method, so that if the actual iteration number exceeds the upper limit that we have established, then that would imply that the variational algorithm will go through more quantum operations than the QFT algorithm. So the results are displayed on the table, the ratio of each operation. And note that the ratios are much more smaller than the actual number of iterations displayed below, which is the actual number of iterations conducted in either non-quantum or quantum manners. Therefore, we conclude that the QFT-based algorithm goes through less quantum operations than the variational algorithm. But for further validation and comparison, for further researches, we should implement a quantum linear solver that solves the matrix equation involved in the QFT-based algorithm. So this is the end of our presentation. Thank you for listening.
Thank you for a nice talk. Any questions from the audience? So you mentioned about the efficiency, but how about the accuracy of the algorithm if you compare the VQA-based and QFT-based? Hello? Still there?
Are you on mute?
Yeah, he is muted. Or not? Not sure. I'm not sure.
Oh, sorry. Can you hear me?
Yes.
Oh, sorry. Suddenly my earphone was connected, so I didn't quite listen to the question. Can you repeat? I'm
Oh,
sorry.
yeah. So you mentioned about the efficiency in terms of the how many runs you need to learn. And what about the accuracy if you compare?
Oh, between the two algorithms, you mean?
Yes.
Okay, so as you see for the L2 norm error in n equals 8 and n equals 16, this is the one for the variational algorithm. So for n equals 8, it was approximately 1.9 times 10 to the minus 3, and for n equals 16, it was 1.2 times 10 to the minus 4. But the QFD one was kind of lower. For n equals 8, it went down to 10 in the ranges of 10 to the minus 4. And for n equals 16, it was a little bit more lower than the variational one. The variational one was 1.2, and the QFT based one was 1.0. And for 32 by 32, we didn't have enough time to convert make until the conversions for the variational one. The QFT based algorithm made it until the ranges of 10 to the minus 5. So basically, the accuracy itself is, we can conclude that the QFT based one is more accurate than the variational one.
Any other questions? If not, let's thank the speaker again. The last but not least is again the World Cup team. So have you figured out how to share your audio with the video? Minjae too? Yeah, why don't you try? If it doesn't work, you can send it to us so we can post it on the YouTube.
University. And today I will present an multi-linking problem protocol for quantum key distribution. This protocol provides a more secure method for key distribution in quantum communications. Let's dive into how this method works and its significance. Today's presentation will cover 4 main parts. First, I will explain the need for quantum key distribution. Then we will explore minking problem. After that, I will introduce the multi-minking problem protocol for Q-KDE. Finally, we will conclude with a summary of the key points. First, let's look at key distribution and why it is important. In classical key distribution, the keys are composed of static bits, which makes them vulnerable to eavesdropping. For instance, if it can intercept the key, and Alice and Bob may never realize it. This is where quantum key distribution comes in. Quantum key distribution uses qubit, so before measurement, if the qubits are in superposed states, it hasn't yet decided on a value. If it tries to measure the qubit, its state collapses and then makes her presence detectable. Additionally, due to the no-cloning theorem, if it cannot clone and or send the qubit without introducing the errors. A well-known example of Q-KDE is BB84 protocol. In this protocol, Alice and Bob exchange qubits using different bases through a quantum channel. If Eve tries to eavesdrop by measuring the qubit, her interference introduces noise, which makes her presence known. Alice and Bob then publicly compare their measurement bases. If their bases match, they keep the qubit and use it to generate a key. If the bases don't match, the qubit is discarded. This process ensures the key is secure, even in the presence of eavesdropper. Now let's move on to the minking problem. The minking problem is complex quantum problem involving quantum measurements, also known as positive operator valued measurements. That is POVM. Here's how it works. Alice prepares an entangled state and sends a qubit to the king. The king measures the qubit using an arbitrary basis such as sigma x, sigma y, or sigma z, and sends it back to Alice. And Alice measures just one time the qubit. The king then informs Alice which basis he used through a classical communication channel. Alice must use this information to deduce the king's measurement result. If there's no noise or interference, Alice can perfectly deduce the king's result. In this slide, I will explain how to solve the making problem, focusing on the case where d equals 2. Let's go step by step on how to solve it. First, prepare an intent state using measurement direction index A. In this step, we create an intent state by combining two different quantum states. Second, after the king's measurement, the quantum state changes. This new state reflects the result of the king's measurement, and the result is represented by B, which can be either 0 or 1. Third, Alice defines a function f that maps value to either 0 or 1. Using this function, she defines a new quantum state based on different possible cases represented by k. From this, we can figure out the king's result by analyzing the sequence of k values. This table shows how k changes based on the measurement index A and the result B. For example, where A equals 0 and B equals 0, the k values are 1, 1, 0, 0. By analyzing this, we can understand how the function f is defined. Using this process, we can determine the king's measurement result and the corresponding states. The multi-minking problem is an extension of the original minking problem where multiple kings are involved. Alice prepares a multi-qubit GHZ state and sends each qubit to different kings. Each king measures their qubit using an arbitrary basis, sigma z or sigma x, and send it back to Alice. Alice measures her qubit allowance. After that, the kings inform her of their measurement basis through a classical channel. Using the information from the classical channel, Alice deduces the measurement result of all of the kings. By repeating this process multiple times, we can increase the probability for detecting eavesdropper. So we can enhance the security and reliability of the key distribution. Then, how to solve the multi-minking problem? In this slide, I will explain how to solve the multi-minking problem, which involves two kings. First, Alice prepares a GHZ state. In this case, she used two types of states, one in the G direction and one in the X direction. Second, each king performs their one POVM. After their measurement, they send the qubits back to Alice, start from the previous measurement basis and result. We create a sequence S, that is J1, I1, J2, I2. Alice then used the W basis for the POVM measurement, which is the same basis as the GHZ state in the W basis. Final step, Alice can deduce the king's measurement result by repeating this process and analyzing the sequence. This table shows the relationship between the W basis and the measurement index J and I. For example, in the case of W equals G, the table shows how the values of J and I change. The areas marked NA indicate that there is no probability for that sequence to occur. For the king's measurement result, and if there is an eavesdropper, it would affect the outcomes, as shown in the table. Now, let's look at how we can implement the minking problem protocol for QKD. Alice prepares a bare state and sends one qubit to the king. The king measures the qubit using one of the bases XYZ and sends the qubit back to Alice. Alice deduces the king's state and repeats the repeat this process multiple times to correct any errors and ensure secure key distribution. To simulate if interference, we can change the initial state or insert a measurement between the king and Alice communication in the quantum circuit that is barrier. And that allows us to observe the impact of eavesdropping. Next, I will calculate the error rate for the MMKP protocol. The error rate gives us an idea of how much noise and disturbance there is in the system if an eavesdropper such as an EVA tries to intercept the qubit. It will impact the error rate. In the first figure, it will intercept a qubit from one of the kings and resend it to Alice. In this case, the error probability is 8 of 1. In the second figure, it will intercept the qubit, performs a measurement, and then resend it to Alice. The error probability depends on two factors, P1 and P2, which represent EVA's interception probabilities. When both P1 and P2 are 1, the error rate is 4 of 1. When both P1 and P2 are 0, the error rate is 32 of 7. This shows how the actions of an eavesdropper can introduce varying levels of errors into the protocol. And the MMKP protocol has both advantages and disadvantages. One of the key advantages is reduced quantum resource usage. Unlike protocols such as BBD4 and minking problem, which require 2n qubits to transmit n bits, but the MMKP protocol only needs n+1 qubits, making it more efficient in terms of qubit usage. Another strength is its high sensitivity to eavesdropping. The protocol can easily detect any unauthorized interception as it is highly sensitive to interference, including eavesdropping attempts. Additionally, the protocol offers simplified communication. After the qubits are distributed, most of the communication involves classical information, making the process more straightforward compared to fully quantum-based protocol. However, there are also some disadvantages. The protocol requires a repetition process to ensure secure key distribution, which can reduce efficiency even though it enhances security. Furthermore, the implementation is complex as it demands precise quantum operations and control, making it technically challenging. Lastly, the protocol is sensitive to error caused by environment noise or operational imperfection, which can impact its overall reliability. I discussed methods for reducing noises and enhancing security in the protocol, as well as some of the challenges involved. One way to enhance security is by using the X, Y, and Z basis instead of us using the X and Z basis. The Y basis is introduced and 2 of the 3 bases are randomly chosen for measurement. This increases the number of possible measurement bases, making it harder for an eavesdropper to gain information without being detected. The useful mature unbiased basis ensures that any eavesdropping introduces detectable disturbance. There are also feasibility and fractional considerations to keep in mind. Measuring in multiple bases particularly the Y basis, is more challenging than X and G because it requires precise phase control. Alice must deduce which basis each king used, whether it was X, Y, or Z. Additionally, the protocol remains sensitive to eavesdropping due to the use of non-commuting bases. Any interception will cause detectable disturbance, allowing eavesdropping attempts to be noticed. And I also discussed how the MMKP protocol can be applied in telecommunication, which presents some challenges but also significant opportunities. First, let's talk about homomorphic encryption. This is an encryption technique that allows to perform operation on encoded data without needing to decrypt it first. Why it is important? It enhances security by ensuring the data remains protected throughout the process, and it reduces telecommuting time. Now, how do I implement and manage this? For encoded data, we need to perform operation without breaking the encryption, which sounds difficult. However, in quantum circuit, unitary operators naturally behave like this. Thanks to quantum universality, these operations don't disrupt the encoded state. So by using quantum states as data, I can implement homomorphic encryption more easily than it might seem. Additionally, I can manage the operations on quantum circuit using machine learning method, which has efficiency and control. As shown in the figure, this is a typical Q-PDE telecommunication scheme. Here, the raw data is encoded using the MMKP protocol, and AI manages the operations on the quantum circuit. The processed data is then sent to the target user, and on the receiving end, the client system uses the shared key to decode the data, ensuring secure communication. In conclusion, the minking problem and the multi-minking problem leverage quantum entanglement and measurement to create a secure protocol for quantum key distribution. The MMKP protocol is highly sensitive to noise and eavesdropping, making it a powerful tool for secure communication. However, practical challenges such as reducing environmental noise and improving implementation accuracy still need to be addressed. Thank you for your attention, and I hope this presentation has provided you with a deeper understanding of how the MMKP protocol enhances the security of quantum communication. Thank you.
Thank you for a nice talk. Can we ask a quick question if there's still any? Okay, so I think the time's up, so I need to wrap up this session. So we had the 4 presentation today from the mentoring program for last around like 2 months. It was designed for 6 weeks, but we had the holiday. And I see there's a lot of the great presentation and also the studies. So I really appreciate all the mentees and mentors for attending this program. And we had the 2 more teams who did not come up today, and they will send us the presentation recorded video, so we can post it on the YouTube. So you can check out our YouTube channel to see the remaining presentations. Okay, so thank you for attending today's session, and thank you for presentation. Thank you for mentoring these teams, especially for mentors, Miguel, Sani, and also Daiwei. Thank you all, David as well. Yeah, thank you.
안녕하십니까. Simulating Ising Model with Hybrid Quantum Deep Learning이라는 주제에 대해 발표하게 될 양자사냥꾼 팀 이호성, 황병호, 김다산입니다. 저희의 컨텐츠는 Background, Method, Result로 간략하게 구성을 하였습니다. 우선 Background에서는 Ising 모델 시뮬레이션을 어떻게 진행하는지, 그리고 이 실험에서 사용된 딥러닝 기법이 어떤 것인지에 대해서 설명하고, Method에 대해서는 우리가 어떤 실험을 진행했는지, Result는 어떠한 결과값이 나왔는지에 대해서 간략하게 소개해 드리도록 하겠습니다. 우선 백그라운드에 대해서 발표하도록 하겠습니다. 우선 이직 모형의 해를 구하는 과정에서 처음으로 선행되어야 할 것이 페르미온, 일단 스핀 형태로 구성되어 있는 트랜스버스 아이징 모델의 해밀토니안을 이런 식으로 페르미온으로 바꿔주는 과정이 선행되어야 하고, 이것을 요르단 위그너 변환이라고 합니다. 이것을 퀀텀 게이트로 구현을 하는 것이 가능하며, 그 후에는 이것을 푸리에 트랜스폼으로 바꿔줍니다. 다음과 같은 수식 과정을 통해서 바꾸어주면 되고, 마지막으로 이 푸리에 트랜스폼 다음에 보글러브 변환을 통해서 이러한 형태로 간략하게 바꿔줄 수가 있습니다. 그리고 지금까지 한 과정에 대해서 역변환을 취해주면 우리가 양자 회로에서 시뮬레이션 하면 되는 회로들을 구성을 할 수가 있으며, 이를 통해서 우리가 해밀토니안이 가져야 하는 고유값을 계산을 하게 될 수가 있습니다. 다음은 저희가 쓴 GFlowNet이라는 모델에 대해서 간단히 소개를 드리겠습니다. GFlowNet이란 이런 식으로 분포를 모델링하는 딥러닝 모델이라고 생각하면 될 것 같고, 저희가 예를 들어서 아이징 모델을 시뮬레이션 한다고 생각을 하면 옵저베이션의 퀀텀 시뮬레이션은 옵저베이션의 분포가 전체 이 스테이트가 된다고 생각을 할 수 있는데, 이것은 그 각각이 시간에 따라서 어떻게 변화를 하는지 그것을 시뮬레이션을 하면서 스텝별로 시뮬레이션을 하면서 이 플로우라는 것이 각각의 스테이트들에 대해서 얼마나 많은 양으로 흘러가는지를 학습을 할 수 있게 되고, 그를 바탕으로 어떤 시간대에서 아이징 모델이 어느 정도의 스핀 변화가 있었고 어떤 형태로 모델링이 되는지 그것에 대해서 분석을 할 수 있는 딥러닝 기법입니다. 다음으로 저희가 진행한 메소드 부분에 대해서 발표를 하도록 하겠습니다. 저희는 간략하게 설명드리면 아이징 모델 시뮬레이션을 퀀텀 컴퓨터를 통해서 돌리고, 그리고 이 Gflow넷을 통해서 데이터 포인트들을 여러 개 뽑는 것을 목표로 하였습니다. 간략하게 설명하면 아이징 모델을 통해서 적은 수의 확실한 값의 데이터들을 생산하고, 이를 통해서 이를 일종의 콜로케이션 포인트로서 사용을 하여 그 퀀텀 컴퓨터로 시뮬레이션 하지 않은 지점에 대해서도 값을 구할 수 있게 Gflow넷을 돌려서 실험을 하였습니다. 저희가 건드려준 것은 리얼드 펑션인데, 우선 에너지를 바탕으로 한 리얼드 펑션을 보통 사용을 할 텐데, 저희는 여기에 퀀텀 시뮬레이션을 통해서 정확한 포인트를 구했을 때 Gflow넷이 돌아가면서 이 부분을 얼마나 정확하게 지나는지를 모델링을 하여서 리얼드 펑션의 두 가지 형태를 만들고 그 두 가지를 합치는 형태로 모델링하였습니다. 각각 값에 앞에 람다 값을 붙이면서 조정이 가능하고, 저희는 0.5, 0.5 정도의 람다 값으로 계산을 하였고 각각의 값 또한 정교화를 해 두었습니다. 이를 통해서 저희는 어떠한 것을 기대할 수 있었냐면, 구해야 되는 포인트가 많아질수록 양자 서킷이 길어지고 실제 양자 회로에서는 노이즈가 증대되는 효과를 낳을 수가 있는데, 일부는 양자 컴퓨터로 정확한 값을 출력을 하고 나머지는 딥러닝, 에너지 모델이 결합된 딥러닝으로 해결을 함으로써 적은 길이의 서킷으로 노이즈를 최소화하면서 많은 양의 데이터를 정확하게 뽑아내는 그러한 것을 저희 실험 목표로 하였습니다. 마지막으로 저희 실험의 리즐트에 대해서 발표를 하도록 하겠습니다. 저희가 계산한 타임 스텝은 0.0, 0.25, 0.5, 0.75, 1.0, 1.25, 1.5, 1.75, 2.0에 대해서 결과값을 내는데 실제 값과 비교했을 때 MSE가 굉장히 적은 값으로 나타났고 실험이 잘 된 것으로 볼 수도 있습니다. 저희가 콜로케이션 포인트로 사용한 것은 이 중에서 0, 0.5, 1, 1.5, 2 이렇게 0.5 간격으로 수행을 하였는데 0.5 간격으로 수행을 한 것 이외에도 굉장히 낮은 MSE가 나오는 것을 보아서 딥플로우넷이 모델을 적절하게 학습을 했다는 것을 알 수 있게 되었습니다. 이상으로 발표를 마치겠습니다. 감사합니다.